Besides the law of conservation of momentum, another general law follows from the equations of motion of a system of point masses that determines the relation between the forces acting in the system and the momenta associated with the torques produced in the system. Let us start our discussion with a system of 2 point masses m1 and m2 with the position vectors r1 and r2 with respect to a reference point O, where the velocities of the point masses are v1 and v2, and their momenta are given by m1 times v1 and m2 times v2. The forces F sub 1 2 and F sub 2 1 are the internal forces acting in the system, and the forces F1 and F2 are external ones applied on the system. Then the first equation of motion of the system states that the derivative of the momentum of the point mass m1 with respect to the time t is equal to the internal force F sub 1 2 plus the external force F1, both acting on the point mass m1. The second equation of motion similarly states that the time derivative of the momentum p2 of the point mass m2 is given by the internal force F sub 2 1 plus the external force F2, both acting on the point mass m1. Here the internal force F sub 1 2 is exerted on the point mass m1 by the point mass m2, and the internal force F sub 2 1 is exerted on the point mass m2 by the point mass m1. Now we take the cross product of the position vector r1 with the first equation of motion, and the cross product of the position vector r2 with the second one. If we add these two equations, then we obtain one equation stating that the cross product of r1 and the time derivative of p1, plus the cross product of r2 and the time derivative of p2, is equal to r1 cross f1 plus r2 cross f2, plus r1 cross f sub 1 2 plus r2 cross f sub 2 1. By applying Newton's third law of action and reaction for the last two terms in the right-hand side, we can write the sum of them as r1 cross f sub 1 2 minus r2 cross f sub 1 2, which gives the cross product of the difference between the position vectors r1 and r2, and the internal force f sub 1 2. Since the vector r1 minus r2 points from the point mass m2 to the point mass m1, it will coincide with the line of action of force F sub 1 2 acting between the point masses. As a result, the cross product in the right-hand side of the equation vanishes, and the sum of the cross products of the position vectors and the equations of motion reduces to the equation stating that r1 cross the time derivative of p1, plus r2 cross the time derivative of p2, is equal to r1 cross f1 plus r2 cross f2. We can follow the same procedure in the general case, and we can prove that for a system of point masses m1, m2, ellipsis, mn at the positions r1, r2, ellipsis, rn, the following equation holds. The sum of the cross product of the position vector ri and the time derivative of the momentum pi of the point mass mi from I equals 1 to n, is given by the sum of the cross product of the position vector ri and the external force fi acting on the point mass mi from I equals 1 to n. The left-hand side can be transformed into another form, if we apply Leibniz's rule for the time derivative of the cross product of the vectors ri and pi, which gives the time derivative of ri cross pi, plus ri cross the time derivative of pi. By definition, the time derivative of the position vector ri is equal to 1 over the mass mi times the momentum pi, that is the first term in the right-hand side vanishes. Now we can substitute this result into the left-hand side of the sum of the cross products of the position vectors of the point masses with the equations of motion for the system. Then we obtain a new equation stating that the time derivative of the sum of the cross product of the position vector ri of the point mass mi and its momentum pi from I equals 1 to n, is equal to the sum of the cross product of the position vector ri and the external force fi acting on the point mass mi from I equals 1 to n. In the left-hand side we see the derivative of an expression with respect to the time, which contains the cross product of the position vector and the momentum of a point mass. We already defined the torque tau produced by a force F acting on a rigid body at a point P described by the position vector r with respect to the center of rotation O, which is the cross product of the position vector r and the force F. The definition can also be applied for a point mass at the point P when we examine its instantaneous rotation about the point O. Similar to the definition of torque, also called moment of force, we can introduce the moment of momentum called angular momentum, a rotational counterpart to linear momentum. The angular momentum L of a point mass m of momentum p with respect to a point O is defined by the cross product of the position vector r pointing from the point O to the point mass, and the momentum p. The angular momentum is a vector perpendicular to the position vector and the momentum with the orientation given by the right-hand rule of the cross product. The unit of the angular momentum is given by the product of the unit of length and the unit of momentum, that is the unit of mass times the unit of length to 2 times the unit of time to -1, which is equal to kilogram times meter squared per second in SI units. In the case of a system of point masses, we can write the angular momentum Li of the point mass mi with respect to the reference point O as the cross product of the position vector Ri of the point mass and the momentum Pi of the point mass. Similarly, the torque tau I produced on the point mass mi by the force Fi is equal to the cross product of the position vector Ri and the force Fi. Then we can define the total angular momentum L of the system as the vector sum of the angular momenta Li of the point masses mi from I equals 1 to n. And the total torque tau produced on the system can be written as the vector sum of the torques tau I of the point masses mi from I equals 1 to n. If we apply the definitions of the total angular momentum of the system of point masses and the total torque applied on the system for the sum of the cross products, then we obtain the following theorem. The derivative of the angular momentum L of a mechanical system with respect to the time t is equal to the torque tau produced by the net force of the external forces acting on the system, where both the angular momentum and the torque are determined with respect to the same reference point O. This theorem holds for any mechanical system, and for a system of n-point masses it can be written as the equation stating that the time derivative of the sum of the mass mi times the cross product of the position vector Ri and of the velocity vi of the point mass mi from I equals 1 to n, is given by the sum of the cross product of the position vector Ri and the external force Fi acting on the point mass mi from I equals 1 to n. As a consequence of the theorem, if the torque tau produced by the net force of the external forces applied on the system vanishes, then the total angular momentum of the system is constant. In the case of a system of point masses, the vanishing sum of the cross product of the position vectors Ri of the point masses mi and the external forces Fi acting on these point masses makes the sum of the mass mi times the cross product of the position vectors Ri and the velocities vi of the point masses constant. This is the law of conservation of angular momentum for any mechanical system, stating that if no external forces act on a system or the torque produced by the external forces acting on a mechanical system vanishes, then the angular momentum of the system is constant. In other words, the angular momentum of a closed system, that is a system in which no external forces are applied, is conserved. As a special case, we can consider a system that consists of a single point mass at the point P described by the position vector R relative to the reference point O, where the point mass has the instantaneous velocity v under the influence of the force F. Then the law states that the cross product of the position vector R and the velocity v of the point mass is constant if the cross product of its position vector R and the force F acting on the point mass is equal to 0. This statement is the reformulation of the law of constant areal velocity, which we already proved in the discussion on elliptic and planetary motion. We saw that the law of constant areal velocity is related to central forces, that is, forces acting on a particle always directed towards or opposite to a fixed point O and given by the magnitude F depending on the distance r of the particle from the fixed point, times the position vector r of the particle relative to the fixed point O. In the case of central motion, the cross product of the position vector r and the force F vanishes, that is, the torque produced on the point mass by the central force is equal to 0. Then the principle of conservation of angular momentum tells us that the areal velocity with the magnitude given by the area A swept out per unit time by the position vector r of a point mass moving along a curve is constant. This is due to the fact that the areal velocity, that is the time derivative of the area vector with the magnitude of the area A and the direction normal to the instantaneous plane of the orbit of the point mass, is given by 1/2, times the cross product of the position vector r and the velocity v of the point mass with respect to the point O. Then the central force acting on a point mass with the constant cross product of r and v gives a constant areal velocity for the point mass. As a result, we can conclude that the law of constant areal velocity is a consequence of the conservation of angular momentum in the case of central motion. Now we examine the relationship between the angular momentum of any rotating mechanical system and the inertial properties of the system with respect to its rotation. Let us consider a rigid body rotating about a given axis with the angular velocity omega, and determine the component of the angular momentum of the body parallel with the axis of rotation. If we choose an arbitrary point O on the axis of rotation as a reference point and attach a coordinate system to the reference point such that its z-axis is the axis of rotation, then we need to determine the z component of the angular momentum L of the rotating body. We already approximated rigid bodies as systems of point masses, where we decompose the body into the set of mass elements represented by the system of n-point masses mi with fixed distances from each other, where our I and vi denote the position vector and the velocity of each point mass mi with respect to the reference point O. Then in the approximation using a system of point masses, the angular momentum L of the rotating body with respect to the reference point O can be written as the sum of the angular momenta Li of the point masses mi with respect to the reference point O from I equals 1 to n, where Li is given by the mass mi times the cross product of the position vector Ri and the velocity vi of the point mass mi. Since the instantaneous position vector Ri of the rotating point mass is perpendicular to its instantaneous velocity vi, the magnitude of their cross product perpendicular to the plane spanned by them is equal to the length of the position vector times the magnitude of the velocity, and the magnitude of the angular momentum Li is given by mi times the product of the length of Ri and the magnitude of vi. In order to determine the component of the angular momentum L of the rigid body parallel with the axis of rotation, we need to compute the z component of the angular momentum Li. If the polar angle theta I denotes the angle between the direction of the angular momentum Li and the z-axis, its component parallel with the axis of rotation can be written as the projection of Li onto the z-axis, that is as mi times Ri times vi, times cosine theta I. We can also write the velocity vi of the rotating point mass mi as the product of the angular velocity omega and the distance di between the point mass mi and the z-axis. Because the angle between the distance vector di and the position vector Ri is a parallel angle of the angle theta I, the distance di can be expressed as the length of the position vector Ri times cosine theta I. As a result, the z component of the angular momentum Li is equal to the mass mi times the square of the distance di, times the angular velocity omega. We can introduce the angular velocity vector omega with the magnitude of the angular velocity of the rigid body rotating about the z-axis, denoted by omega z, and with the direction of the axis of rotation or the unit vector Ez. The magnitude of the angular velocity vector can be either positive or negative depending on the direction of rotation of the body. Then in the general case, the z component of the angular momentum Li given by plus or minus mi times di squared times omega, is equal to the mass mi times the square of the distance di, times the z component of the angular velocity vector omega. Now we are able to determine the z component of the angular momentum of the rotating body given by the sum of the angular momenta Li of the point masses mi from I equals 1 to n, and write it as the z component of the angular velocity vector z describing the rotation of the body, times the sum of the point mass mi used to approximate a given part of the body, times the square of the distance di of the point mass mi from the axis of rotation from I equals 1 to n. In this expression the component of the angular momentum parallel with the axis of rotation is equal to the product of omega z describing the rotation, and a sum depending only the mass distribution of the system of point masses approximating the body around its axis of rotation. We call this sum denoted by capital I, the moment of inertia of the system of point masses or the rigid body with respect to the axis of rotation z. Its definition shows that the greater the mass of the point masses and the greater their distance from the axis of rotation, the greater the moment of inertia of the point masses distributed around the axis. In Cartesian coordinates the square of the distance di of the point mass mi from the z-axis is given by the sum of the squares of the x and y coordinates of the point mass mi. The unit of the moment of inertia I is the unit of mass times the square of the unit of length, that is kilogram times meter squared in SI units. By virtue of this definition, the z component of the angular momentum L of the rotating body can be written as the product of the moment of inertia of the body with respect to the z-axis, and the z component of the angular velocity vector omega. We note that if the mechanical system consists of more bodies rotating about the z-axis with the angular velocities omega sub 1z, omega sub 2z and so on, and the moments of inertia of the bodies are I1, I2 and so on with respect to the axis of rotation, then the z component of the angular momentum L of the whole system is given by I1 times omega sub 1z, plus I2 times omega sub 2z and so on. Let us consider some experiments and examples illustrating the concept of moment of inertia of rotating bodies. In the first experiment we use a toy train on a track mounted on a bicycle wheel free to rotate about its fixed vertical axis, where the train and the wheel are initially at rest. By turning the power on, the train can be set in motion while the wheel starts to rotate in the opposite direction. If friction is neglected, the external forces acting on the system formed by the toy train with its track and the wheel, do not produce torque with respect to the axis of rotation of the wheel pointing in the direction of the z-axis. That is, the z component of the torque produced by the external forces vanishes. Then the law of conservation of momentum tells us that the z component of the angular momentum L of the system is constant, and it must be zero if it was zero initially at rest. Let I1 denote the moment of inertia of the toy train with respect to the z-axis, and omega sub 1z denote the z component of the angular velocity vector of the moving train with respect to the lab frame. Similarly, let I2 and omega sub 2z denote the corresponding quantities for the wheel. We can write that the moment of inertia I1 times the angular velocity omega sub 1z, plus the moment of inertia I2 times the angular velocity omega sub 2z vanishes. Here the z component of the angular velocities ω1 and ω2 have opposite signs since they describe rotations in opposite directions. Then the absolute value of the ratio of ω sub 1z to ω sub 2z is equal to the ratio of I2 to I1. In other words, the ratio of the angular velocities of the train and the wheel is inversely proportional to the ratio of their moment of inertia. For a given angular velocity of the train, the angular velocity of the wheel is proportional to the moment of inertia of the train but inversely proportional to the moment of inertia of the wheel. In another experiment demonstrating the law of conservation of angular momentum, a student is sitting at rest on a revolving stool while she holds a pair of weights in her folded arms. The stool is set in motion by another person and we assume that the angular velocity omega of the system formed by the student with the weights and the stool is approximately constant. However, if she suddenly outstretches her arms with the weights, the angular velocity of the system will decrease. We interpret the result of the experiment in terms of the torque produced by the external forces acting on the system. By neglecting friction, we can assume that the component of the torque parallel with the axis of rotation vanishes, that is, the moment of inertia I of the system times its angular velocity omega is constant. When the student extends her arms holding the weights, she increases the total moment of inertia of the system, resulting in the decrease of the angular velocity of the rotation. By pulling her arms close to her body again, she reduces the moment of inertia I, which speeds the rotation of the system up to its initial angular velocity. Another demonstration of the conservation of angular momentum in the system is when the student sitting on the revolving stool holds a bicycle wheel with its axis pointing in vertical direction. If the student starts to spin the wheel, then she and the revolving stool are also set in motion and rotate in the opposite direction. If the student stops the spinning wheel, then the stool stops rotating as well. The interpretation of the result of the experiment is the same as in the previous demonstration. That is, the change in the moment of inertia of the whole system forces to revolve the stool or to stop the revolving stool due to the conservation of the angular momentum of the system. Now let us suppose that the wheel is spinning and the stool with the student is revolving with a constant angular velocity as seen in the image. If the student tilts the wheel such that the angle between its axis of rotation and the vertical direction is 45 degrees, then the stool will slow down and revolve with a lower angular velocity. If the axis of rotation of the wheel becomes horizontal, then the stool will even not revolve at all. From both the demonstrations we can conclude that the angular momentum vector L of the wheel spinning about its axis of symmetry is given by the product of the moment of inertia I of the wheel and the angular velocity vector omega, and only the vertical component of the angular moment L has an effect on the rotation of the stool. A further demonstration can be made in the experiment with the revolving stool and the spinning wheel. If the student sitting on the stool at rest takes the wheel spinning about the vertical axis into her hands, then the stool remains at rest. However, if she flips the spinning wheel upside down such that he wheel spins in the opposite direction, then the stool starts to revolve. If the student turns back the wheel into its original position, then the stool stops revolving. The interpretation of the results is the following. When the student takes the spinning wheel in her hands, the system formed by the student, the stool, and the wheel gains the z component of the angular momentum L of the wheel, which is positive. This amount of angular momentum must be conserved since the z component of the torque tau of the system vanishes. However, when the spinning wheel is turned upside down, its angular momentum changes from plus L to minus L, that is, the change in it is equal to minus 2 times L. The law of conservation of angular momentum causes for the student with the stool to start to revolve so that they can gain the angular momentum of 2 times L, which holds the total angular momentum Lz of the system constant. The student sitting on the revolving stool at rest can also rotate the stool by applying internal forces. For example, if she raises one of the weights in her hands over her head and circle with the weight, then the stool starts to revolve in the direction opposite to the direction of the motion of the weight along its circular path. The revolving stool can even be rotated by a given angle without using the weight if the student repeats the following sequence of motion with one of her arms. She spreads out one arm forward and moves her outstretched arm behind her back in the horizontal plane, then folds it. Falling cats released from rest upside down produce similar motion. They can rotate about their horizontal axis through 180 degrees by using their legs or tail and land on their feet. An athlete swinging around a horizontal bar can increase his angular velocity at the proper moment, if he decreases the moment of inertia of his body with respect to the axis of rotation by compressing his body towards the bar. An interesting example is the possible variation in the angular velocity omega of the rotating Earth based on the situation illustrated in the second experiment, where the product of the moment of inertia I and the angular velocity omega is constant for a closed system. The variation in the speed of Earth's rotation might be due to some change in the moment of inertia of the planet. However, Such a change must be cataclysmic in order to produce a non-negligible modification in the velocity of the rotation of Earth. Following the example described in the first experiment, the angular velocity of Earth could also be changed if millions of vehicles simultaneously traveled in the directions parallel with the equator from west to east, that is in the direction of the rotation of the Earth. Although the solar system is generally considered as an open system exchanging energy and matter with its environment, it can be approximated as a closed system in many calculations related to celestial mechanics. Therefore, the magnitude and the direction of the angular momentum L of the solar system is constant. The plane perpendicular to the total angular momentum L and passing through the barycenter of the solar system is called the invariable plane of the system. The normal of this plane has a constant direction with respect to any inertial frame of reference, and in turn the invariable plane can be chosen as one of the coordinate plane of the inertial frames in astrometry. Our last example is the Segner wheel consisting of a vertical cylinder and one or two pairs of bent pipes with nozzles attached to the bottom of the cylinder. If the cylinder is filled with water, then the fluid is ejected from the nozzles due to the hydrostatic pressure, which produces torque on the wheel causing its rotation. In a Segner turbine the working substance is normally steam, and the torque produced in such a system can be transmitted to a working device through a mechanism using belts and pulleys. The rotating motion produced by such wheels or turbines can be described by applying the law of conservation of angular momentum in a way similar to the one presented for the principle of propulsion.